Okay, so today we're going to continue with parametric curves. So last time we looked at the definition for a parametric curve. Okay, and we looked at sketching and identifying how to do the different sketches. Today we're going to look at some of the calculus involved. So tangents, tangent vectors, and so on, things like that, tangent lines. And we're going to look at a physics example. So looking at the position vector, the velocity vector, acceleration vector, and the force vector. So if we imagine the parametric curve as a particle moving around in space, then the tangent vector will correspond to the velocity vector, and so on. Okay, we'll look at those examples. Okay, so firstly, we're going to be looking at the tangent line. So we've done tangent lines before. So last year when we did the implicit differentiation, now we're going to look at tangent lines again, but for parametric curves. Okay, so first section for today, tangent lines of parametric curves. Okay, so let's say we have some parametric curve given by x of t and y of t, and maybe it looks something like this. Okay, so we know parametric curves can look quite weird. So let's say we've got this parametric curve here, and at this point over here, let's call that point P, we are interested in the tangent line. Yeah, there's going to be some tangent line to the curve at point P. What is the equation of that tangent line? Now, we're not given the curve in terms of x and y. We're given the curve in terms of x of t and y of t. So how do we then find the tangent line? Okay, well, the first thing to do when finding the tangent line is finding the gradient. Okay, so we want to find y prime or f prime at that point P. So let's say we can write this curve as y is equal to f of x. Yeah, but we know that it's not y as a function of x. We know y is y of t and x is x of t. So we can write this as y of t is equal to f of x of t. Okay, because we know that they're both functions of that curve parameter t, or time, if you want to think about it like that. Now we want the derivative, so let's do d by dt on both sides. So we're going to have d by dt of y of t is equal to d by dt of f of x of t. Yeah, right, we want the gradient, so we need to do the derivative. Now d by dt of y of t, we can write that as dy by dt. And now on the right-hand side, we need to use the chain rule, because we want d by dt of f of x of t. So we have f of x of t, we need to use the chain rule. So it's going to be f prime of x times, and then by the chain rule, the derivative of the inside, that's going to be dx by dt. Okay, now we're just going to change the notation a bit, just to make things a little bit easier. Dy by dt, we can write as y dot. And we still have f prime of x. And dx by dt, we can write that as x dot. Okay, so it's a little bit of change of notation, but it just helps simplify the next line. So we're going to take the x dots over to the other side. So we end up with f prime of x is equal to y dot over x dot. Okay. It's a little bit neater than writing dy by dt divided by dx by dt. So it just saves us doing the fraction over a fraction. But if you want to write this as dy by dt over dx by dt, you can do that. Okay, but y dot over x dot, it's a bit neater. Okay, now f prime, that's the derivative at x. In other words, that is the gradient of the tangent line. So we have the gradient of the tangent line. That will be m. which is f prime of x. We know that from before. And then that will be y dot over x dot. Okay. And then we know the equation of a straight line. So let's say this was at the points a comma b. Then we would write y minus b is mx minus a. Right, if you're interested in the tangent at AB, that's your straight line equation. Okay, any questions so far? You're all good. Okay, let's have a look at an example. Okay, so we're given a parametric curve and we want to find the tangent line. Okay, so example, find the tangent line to the parametric curve Okay, so this will be given as some x of t and y of t. So x of t, that's given by t to the 5 minus 4t cubed. And then y of t, that's given by t squared. Okay, so we're not doing any 3D cases yet. Okay, so all of this is still under the 2D parametric curve section. Okay, 3D, that will come later. Okay, so again, when you're looking at the June test breakdown and the final exam breakdown, all of this is under 2D. Okay, not 3D. 3D, we will cover that next week. Okay, so we have this as our parametric curve at the point 0, 4. Okay, so at this point, what is the tangent line? So step 1, find the gradients. Okay, and we know that the gradient is going to be y dot over x dot. So let's work out what those are going to be. So x dot, that's going to be 5t to the 4 minus 12t squared. So that's just doing the time derivative for x. And then y dot, that's going to be 2t. Okay, and then the gradient m, that will be y dot over x dot. But we need the t value. We don't know what that is yet. Okay, so we need the t value to find x dot and y dot. Right, so once we substitute the t value, then we can do y dot over x dot, and that will give us the m value that we need. So how are we going to find t? Well, we're given the equations for x and y, and we're given the points that we're interested in. So from the point, we can see that x will be 0 and y will be 4. So we can take x is 0, y is 4, substitute it into the parametric curve equations, and solve for t. Once we have t, we can then find the gradient. Okay, so we know that the x must be 0. So we're going to have t to the 5 minus 4t cubed is 0. So that's from the point. And the y value was 4. So t squared must be 4. Okay, so this first one, that was the x value. And the second one, that was the y value. Okay, now we can just solve these two for possible values of t. Let's do the second one. Okay, that's quite easy. If t squared equals 4, then t must be plus or minus 2. Okay, that was quite easy. The first one, we can take out a t cubed. So we have t cubed, then we're left with t squared minus 4 is 0. So we get t equals 0 or t equals plus or minus 2. Now notice between the two equations we have an and, right? So the first one must be true and the second one. In the first case, we get t equals 0, but in the second one, we don't get t equals 0. So that is a non-solution, right? NA. Okay. But the first one has t equals plus minus 2. So that's t equals plus minus 2. And the second one also has t equals plus minus 2. So those are valid solutions. So valid t solutions, that will be t equals minus 2 and t equals plus 2. So it appears at that point we have two tangent lines. Okay. Now in the normal case, we don't have two tangent lines, we only have one. But we'll see in this case, there's going to be a special self-intersection with the curve. And we'll see that there's two tangent lines. Okay, so this isn't a mistake. We do have two tangent lines, and we'll see what that looks like later. So we have two tangent lines. Okay, so you might get one tangent line, you might get two tangent lines. Okay, so one of the tangent lines will be at t equals minus 2, and the other tangent line, that will be at t equals plus 2. Okay, so let's look at the t equals minus 2 case. So t equals minus 2. So what we want to do is find the gradient and then find the equation of the line. So let's do the gradient first. So m, that will be y dot over x dot. And we're going to substitute t equals minus 2. So you can check that. You just substitute t equals minus 2, and we get minus 1 over 8. Okay, so that's the gradient. What is the tangent line going to be? Well, we know that this is happening at the point 0, 4. So we're going to have y minus 4 is going to be minus 1 over 8 x minus 0. Okay, just your normal straight line equation. So we have y is equal to minus 1 over 8x plus 4. Okay, so that is our first tangent line. What about the second tangent line? So that was happening at t equals plus 2. So again, we're going to have m. That will be y dot over x dot. Okay, and we're going to substitute t equals plus 2. So this is going to give us 1 over 8. You can check that. Okay, and again, this is happening at the point 0, 4. So we're going to have y minus 4 is 1 over 8 x minus 0. Okay, so y equals 1 over 8x plus 4. Okay, so we have our two tangent lines there. Now, like I said earlier, this is a bit weird having two tangent lines. Normally, we only have one tangent line. But let's see what this curve looks like. And we'll see that there's a self-intersection point, and that's what gives us the two tangent lines. Okay, you should all be familiar with Desmos at this point. Please make sure you use it for your curve plotting. Okay, so let's plot the curve. So we're going to have our x, that's the first part of the point. That was 5t to the 4 minus 12, minus 4. So t to the 5 minus 4t cubed. Okay, so that's the x part of the point. You can just put a comma, and then the y part of the point, that was t squared. Okay, let's say we go from minus 5 to 5, something like that. Okay, so we end up with this. And notice at this point 0, 4, let's just put that point there, 0, 4, we see that the curve intersects itself. So going from left to right, we go from the left, we go through that point, we go around, and then we go through that point again. So that point there at 0, 4, we go through it twice. Does everyone see that? Yeah. So let's see the first tangent line. So that was y equals minus 1 over 8 plus 4. X, there we go. Okay, so we have this green tangent line going along there. So we move along, we go through that point, and we get the green tangent line. we continue through the loop, we go through it a second time, and that will give us y equals 1 over 8x plus 4. And that now gives us the purple tangent line from the second time that we go through the points. So we'll just zoom in again here. So again, from left to right, we go through the points the first time. That gives us the green tangent line. We go around the loop down to the origin, back to the point, through the point a second time, and that gives us the purple tangent line. Okay, so we get 2 tangent lines at that point. But if we look at another point, like over here, if you can see over here, we're only going to have 1 tangent line. Okay, so it depends on where you are. But if there's the self-intersection point, you're going to have 2 tangent lines. Does everyone see that? Okay. Okay, some homework. Okay, so 2 questions on this. Number 1. Given the parametric curve, okay, x of t and y of t. Again, we're still dealing with the 2D case. So x of t, y of t, find the equation for the second derivative of y with respect to x. So we've done the example for dy by dx. Okay, that was the f prime gradient for the tangent line. Now, to do a similar thing, but for the second derivative. Okay, so what is that going to be? Okay, so this will be in terms of x dot, y dot, x double dot, y double dot. Okay, you'll have a look at that. Okay, and then number 2, find the tangent line. Find the tangent line to the parametric curve. Okay, we have x is equal to 2 cos 3t minus 4 sine 3t, and y is equal to 3 tan 6t. Okay, so we've got x and y. Again, still the 2D case. At t equals pi over 2. So for this example here, I don't give you the point AB. Instead, I give you the t value. But once you have the t value, you can substitute it into x to get your a, and you can substitute it into y, and that will give you the AB point. Okay, so 2 different ways of asking that question. Good. Any questions on tangent lines? All good. No questions. Okay. Next, tangent vectors and curvature. Okay, please do not mix up tangent line with tangent vector. Okay, they're very similar. Okay, we know what the tangent line is. That's the whole line passing through that point. And we know what tangent vectors are, right, from physics. Okay, please don't mix them up. Okay, so let's say we've got our parametric curve again, maybe something like this. We have our point P over here, and we have our tangent line. Okay, so we know how to do the tangent lines. Now, the tangent vector, that is a vector from P, and it lies along the tangent line. Okay, so very similar. tangent line and tangent vector, but again, please do not mix them up. Tangent line, that is the whole line that passes through P and touches the parametric curve. A tangent vector is a vector along the tangent line at P. Okay, so tangent vector is a vector, tangent line, that's a line. Okay, please don't mix them up. Okay, so we're not going to be looking at this in terms of tangent vectors and so on. We're going to look at it more in terms of the physics side. So on the physics side, the parametric curve is like the position of a particle, and the tangent vector, that will be the velocity vector of the particle. Okay, so same idea, but we're going to look at it more in terms of the physics side. So we will look at this from the physics side. Right, so we're going to be dealing with positions of particles, velocity, acceleration, forces, and so on. Okay, but you must always keep in mind this picture, okay, with the tangent vector along the tangent line. Okay, so in physics, if we treat the parametric curve as the particle moving through space, then the position that is given by the r vector. Okay, we put the little arrow at the top for a vector. Okay, this is given by x of t, y of t at some point, right? So your position is just some point at some time. Now, we could have also written this as x of t I hat plus y of t j hat, right? Your unit vectors in x and y directions. Okay, then we have the velocity. So that is r prime of t. Okay, but we give it a special name, v, for velocity. Okay, and this will be x dot of t, y dot of t. And this will be the velocity vector, also the tangent vector. So this blue vector over here at the point P, that is the velocity vector of the particle at P. Okay, and again, you could have written this as x dots of t I hat plus y dots of t j hat. Okay, and if you were working in 3D, you would have I hat, j hat, k hat. Okay, you know all of that. Okay, then the acceleration. So that will be r double prime. So a second derivative of position, that gives you the acceleration. We call that a. So that will be x double dots of t, y double dots of t. Again, or you could write it in terms of the unit vectors. So that will be x double dots of t I hat, y double dots of t j hat. And if you had z, you would put z double dots k hat. Okay, and finally, the force. Okay, that's just your mass times acceleration. So once you have your acceleration vector, then your force vector is just mass times acceleration. Okay, yeah, you know all of that stuff there. Okay, let's look at an example. Okay, there's going to be two parts to this. So a particle of mass m is moving around a circle at constant angular velocity. Omega. Okay, so it's going around in a circle, constant angular speed or angular velocity. Okay, part one. find the velocity vector as it goes around the circle. Okay, and number 2, show that the acceleration is perpendicular to this velocity vector. So velocity vector, and provide a sketch. Provide a sketch of the motion and these two vectors. Yeah. So 2 parts. Number 1, find the velocity vector. So we know that it's moving around a circle. So at some point, whatever that point is, what is the velocity vector going to be? And then we need to sketch that. And then part 2, show that the acceleration vector is perpendicular to the velocity vector at any point going around the circle. Okay, so let's do number 1. So to find the velocity vector, first we need the position vector, and then we're going to do the time derivative. So the position vector r of t, I'm going to use the I and j unit vector notation, but you can use whatever you want. So going around a circle, so it's going to have some x and some y, right? Because it's in 2D. So it's just going to be some x and y. Now, if it's going around a circle, we know what x and y are going to be. So x, that's going to be r cos omega t. Okay, because it's got constant angular velocity. So r cos omega t plus, and then for y, that will be sine. So r sine omega t. J. Okay, so that's the position vector. What about the velocity vector? So we need to do the time derivative. So the velocity vector v, that's going to be r prime of t. Okay, so the derivative of cos, that's going to be minus sine. We take the omega out. Okay, plus, and then the derivative of sine, that's going to be cos, and we take the omega out. Okay, so we got the velocity vector. Okay, then for part 2, show that the acceleration is perpendicular to this velocity vector. So part 2, we need the acceleration vector, so a of t, that will be v prime. Okay, so the derivative of sine, that's going to be cos, and then we take out another of the omegas. So minus r omega squared cos omega t. Okay, and then the derivative of cos, that's going to be minus sine. So that will be minus r omega squared sine omega t. Okay. So here we have the acceleration vector. Now, what we want to show is that the acceleration vector and the velocity vector, those are perpendicular to each other. So if I have 2 vectors and I want to show they're perpendicular, what do I need to do? Yep. Not the cross product. Yep. You could do that. Yeah, you could do that. That's one possibility. That's a bit longer because then you need to find the tangent line and the normal line. It's a bit extra work, but you can do that. I'm looking for a simpler method. Got 2 vectors. I want to show that they are perpendicular. Yeah. Sorry? Vector addition. Not quite. Getting closer. Come, points available. Think about it. Yep. Not quite. Yep. Dot product. Yeah, you get the points. Well done. Yeah, we're going to do the dot product. So we've got this vector here, and let's say another vector here. Let's say U and V. We'll do the dot product between them. Right. So here, if we have this angle theta, we know that the dot product is U times V cos theta. If theta is pi over 2, then the dot product will be 0. Okay, so they'll be orthogonal. Okay, so we're going to do the dot product between them. So for homework, try the other way. Find the tangent line and the normal line. Check the gradients. But this way is much easier. Okay, but again, up to you. You can do it the long way if you want. But this is quite quicker. Okay, so we're going to have A dot V. So that's going to be minus R omega squared cos omega T I hat plus, minus R omega squared sine omega T J hat. Okay, dot product with the V that we had earlier there. So that's going to be minus R omega sine omega T I hat. And then the plus R omega cos omega T J hat. So we're just going to do the dot product between these. Okay, so this is going to be plus R squared omega cubed sine omega T cos omega T minus R squared omega, omega there, R squared omega cubed sine omega T cos omega T. But these are the same, just with the minus sign, and that's going to be 0. Okay, if the dot product is 0, that means they are perpendicular to each other. Okay, and then the last bit of the question, provide a sketch of these vectors to show that they're orthogonal. So let's draw a little picture. So we have X and Y. So the particle is going to go around just a circle there. So let's say it's over here. Okay. It can go either way around. It doesn't really matter. But the way that we set it up, it's going to go counterclockwise around. So the velocity vector is going to be tangent, like that. Okay. And then the acceleration, remember that comes with the minus sign, so it's going to be pointing inwards, and the acceleration is going to be like that. Okay, and these are orthogonal. Okay, remember the minus sign on the acceleration, so it's going to be going inwards like that. So we got the velocity vector in blue going tangent. Okay, remember velocity vector and tangent vector. And then in this case, we've got the normal vector, that is the acceleration vector. And we can see they are orthogonal. Any questions on this? You're all good. Okay, so the remaining examples, that will be in the tutorial. Okay, so just have a look at those tutorial questions for these examples. Okay, any questions before we move on? You're all good. Okay, so all of this should be familiar from physics. This is just a quick recap. Okay, anything before we move on? Okay. Okay, so you might have seen this in physics, maybe not, but we'll go through it again. and that is the curvature. Did you cover curvature in physics? Like if you have the magnetic field and the particle makes a little loop with some curvature, did you cover that? Maybe. Okay. So let's say we've got the motion of a particle like we had before. Okay, maybe it's doing a loop. It doesn't have to be a loop. But what we're interested in is at some point, what is the curvature of that path? So here we've got some point P. There's going to be some velocity vector. Okay, so if there were no forces involved, we know that the particle will just carry along on a straight line. So it will carry on along the tangent line. So no forces, it just moves along the straight line there. Now, if there's some forces involved, it's going to deviate from that straight line. So there's going to be some force here. Let's put that in green. Some force F, and that's going to pull the particle away from that straight line. Okay, and there's going to be some curvature there. So if you're going in a straight line and you suddenly start turning off in a direction, you see that as curvature. Now, you would know that from centripetal acceleration. Okay, if you're going around a bend, there's going to be that centripetal force pulling you out of the bend or into the bend. You've done that in physics, right? You have done that, yeah. So that force is going to pull you away or into the bend. So centripetal inwards, centrifugal outwards. Now, the amount of force or the amount of bending, that is given by the curvature. So if you make a very small bend, there's going to be a very large force pulling you. If it's a very shallow bend, like this one over here, very wide bend, then the force is going to be much smaller. Okay. And the way we differentiate between those two is with the curvature. Okay, so the force or forces, okay, moving you around a bend. Okay, is related to the curvature of the bend. Yeah. And again, you can just keep in mind, if you have like a very little circle, there's you moving around. Okay, so a very small circle, that's going to have a very high curvature. So as you go around, it's going to be quite a rapid bend. But if you have a very large circle, again, there's you there, you moving around. It's not as sharp of a bend. Okay, so a very small circle, very large bending, a very large circle, a very small bending. Okay, so just keep that in mind when we look at curvature. Okay, and again, in both of these cases, this vector is v. That's your velocity vector or your tangent vector. Okay, so definition. Before we get that, everyone okay with the two pictures? Okay, small circle, large curvature, big circle, small curvature. Everyone's okay with that? Okay, so definition. The curvature K at a point is given by K is equal to the length of this vector. So we use absolute value, for the length of the vector. Capital T hat prime at T divided by the length of the velocity vector. So you know r, that's your position, r prime, that's your velocity. What is this t hat? So t hat is the unit tangent vector. Okay, so wherever you are, you can calculate the tangent vector, t, and then t hat, that is the unit tangent vector. So you know I hat, j hat, k hat, those are your unit vectors for x, y, and z direction. T hat, that is the unit vector in the tangent direction. And then, you know, r, that's your position vector. Yeah. So you take the ratio of these two, and that gives you the curvature. Okay, so we can calculate this in 4 steps. Calculating the curvature. Okay, step number 1. Find r prime of t and the length of r prime of t. Or you can think of it as find the velocity and then the length of the velocity vector, that's your speed. Right, because we're trying to think of this in terms of the physics side. So r prime, remember that is your velocity. And then the length of the velocity vector, that's the absolute values sign there, that is the speed. Okay, so you've got your velocity vector and you've got your speed. Okay, so that's step 1. Step 2, find the unit tangent vector, t hat. That's going to be the velocity vector divided by the speed. Okay, so if you take the velocity vector and you divide by the length of the velocity vector, then the length is just 1. So just look at a little picture here. So again, we're interested in this point here. If you've got the velocity vector v, and you take that velocity vector and you divide by its length, then you're going to get the unit vector in that direction, v hat. Okay, so this has length 1. Okay, so that's step 2. So you find the unit tangent vector. So that is the velocity vector divided by the length of the velocity vector. Okay, step 3. We need the derivative of this vector now. Okay, so we're going to find t hat prime and the length of this vector. Okay, whatever that might be. Okay, so that's step 3. So step 3, take the derivative of whatever you got there from step 2. And then finally, step 4, put everything together. So k, that is going to be the length of the unit tangent vector, prime, so the derivative of that, divided by r prime of t. Sorry, that's of t. Okay, and then remember that was just the speed. Okay, so 4 steps to find that. Any questions on the steps? Okay, so we'll go through it one more time. So number 1, find your velocity and the speed. Number 2, divide the velocity by the speed to get a unit vector in that direction. Step 3, take the derivative. And then finally, step 4, take the length of that and divide it by the length of the velocity vector or the speed. So this bottom part, that's the speed. Okay, any questions? Yeah. T, that is the velocity vector divided by its length. So you're taking the vector, you're dividing by its length so that the length becomes 1. So you can think of it as v hat is the velocity vector divided by the length of the velocity vector. Okay, that is this t hat here. Okay, and again, the little hat thing there, that just means length 1. Okay, any other questions? You're good. Okay, let's have a look at an example. Okay, so we've got some particle moving around. We want to know what is the curvature when it bends around. So find the curvature at t for the parametric curve. Okay, and then we've got here x is t and y is t squared. Okay, so a very simple curve. Okay, so we know this is going to be some kind of parabola. So if x is t and y is t squared, this is going to be y equals x squared. That's going to just be the parabola. Okay, so the particle is going to move around in this curve. So there's going to be some force acting on the particle. You can work out what that's going to be for homework. And whatever this force is, that is what's causing it to make this bend. And we want to know what is the curvature at t. Okay, at some time t, there's going to be some curvature due to that force. Okay, so let's follow the steps. So step number 1, we want to find the velocity and the speed. So the position vector, that's going to be given by t I hat plus t squared j hat, right? Just x I hat plus y j hat. Now we need the velocity, so that's r prime. That's just going to be a 1 I hat plus 2t j hat. Okay, so that is the velocity vector. The speed is going to be the length of this vector. So that's going to be the square root of 1 plus 4t squared. Okay, so we've got the velocity vector and we have the speed. Step 2, we want to find the unit tangent vector. So that is the velocity divided by the speed. Okay, so again, that's the velocity from line 2 divided by the speed in line 3. So that will be 1 over root 1 plus 4t squared I hat plus 2t over root 1 plus 4t squared j hat. Okay, so that is our t hat. Again, velocity divided by the speed. Step 3, we need t hat prime. So we're going to do the time derivative for the x part and the time derivative for the y part. So we're going to end up with minus 4t over 1 plus 4t squared to the 3 over 2 I hat. So that is the derivative of the x part. And now we need the derivative of the y part. That's going to be plus 2 over 1 plus 4t squared to the 3 over 2 j hat. Okay, so that is taking the derivative of the x part of t hat and then the y part of t hat. Okay, now we need the length of this. So the length of t hat prime, that is going to be the root of the x part squared plus the y part squared. We're going to end up with 2 over 1 plus 4t squared. Okay, so you can check that out. So that's just the first part squared plus the second part squared, and then we just take the roots. Okay, and then finally step 4. So we just take this last thing we found and divide by the speed. Okay, so that will be t hat prime divided by the speed, which we did in step 1. Okay, so we're going to take this last part and then divide it by the speed from the first part. So this is going to be 2 over 1 plus 4t squared. And then we're dividing by the speed here that we found in the first part. So that's root 1 plus 4t squared. Then we can combine the bottom together. So that's going to be 2 over 1 plus 4t squared to the 3 over 2. Right, that's just the 1 plus the half. We get 3 over 2. Okay, so that is the curvature. Now, if you were to substitute different values of t, you would then get the curvature at different points or at different times. Okay, for example, at t equals 0, wherever the particle t equals 0, so the bottom point over here, the curvature over there will be 2. Okay. Any questions on this? Okay. Yeah. Step 3. So step 3 is we're just taking the derivative of these two parts. So we got the blue part and the pink part. So I'll do the first one and then you can do the other ones. So we want d by dt of that first part. So the root is in the bottom, so we can write it as a minus a half exponent. So 1 plus 4t squared to the minus a half. Okay, we're going to take the minus half down. 1 plus 4t squared. Minus a half minus 1, so that's minus 3 over 2. Times, and then chain rule, derivative of the inside, that will be 2 times the 4, so that will be 8t. Okay, then the minus can stay. 8 over the 2, that will be a 4. So we have 4t. And then the minus 3 over 2, we can put that to the bottom. Okay, and then that will be the blue part here. Yeah, and that's the same for the pink part. All right. Any other questions? All good. Okay. So this is one definition of curvature. So this one over here. Okay, that's one way to define it in terms of like the speed of the particle and the changing velocity vector. There is another definition depending on the tangent line and the angle that it makes with the horizontal. Okay, you get exactly the same answer. It's just another way to define it. Sorry. So another definition of curvature. Yeah, again, they're exactly the same, just looks a bit different. So here, we're going to have the curvature K is given by d phi by ds. And then we do the absolute value. So if you leave out the absolute value, that is called the signed curvature. What that means is just if you have the curvature this way, for example, with some radius, that's going to be positive curvature. But then if you flip it and you look on the other side, then it's negative. Okay. So here, this is positive curvature. Okay, and then if you flip it around, then that gives you negative curvature. But we're not going to be interested in positive curvature and negative curvature. We're just going to put the absolute value. Okay. So the absolute value, that just gets rid of the sign. So we go back to what we had before. Okay, so what is phi? So phi is the angle of the tangent line. Okay, so remember the previous definition for curvature, that was with the tangent vector and the length of the tangent vector. Now this definition uses the tangent line. Okay, a little bit different, but we end up with the same answer. And S is the curve length. Okay, so we won't need to worry too much about curve length. That will come later on next week. But for now, we won't need to worry about that too much. Okay. But next week, we'll be looking at this in a lot more detail. Okay, so let's draw a picture of what's going on. So we got some sort of curve. Maybe it's doing that. And we want the curvature at this point. Okay, let's call that P. Okay, so what we do is we draw our tangent line. Okay. And this angle phi, that is the angle of the tangent line. You know, your tan theta equals m. You know, you did that in high school. So here is phi. Right, you know, tan phi is m or tan theta is m. Okay, you covered that before in high school. Yeah, so what we want to do is figure this out and end up with a different equation for the curvature. And then for homework, you're going to show that that is the same as the previous definition. Okay, so we want d phi by ds. Now, doing it like that is going to be a little bit more difficult. So instead, we're going to use the chain rule and write d phi by ds as d phi by dt, dt by ds. Okay, so here we just use the chain rules. So d phi by ds is d phi by dt. Okay, we've used t before. We know how that works. And then dt by ds, that's a problem for later. We'll do that later on. So this is just using the chain rule. Okay, d phi by dt, we can work with t, dt by ds. We'll save that problem for later on. Okay, so d phi by dt, what do we do? Well, we know that tan phi is the gradient, and we know how to find the gradient. We did that at the beginning of the lesson. So tan phi is the gradient, and we know the gradient is y dot over x dot. Right, that was from way in the beginning. Here we want d phi by dt. But currently we've got tan phi. So let's do arctan on both sides. So phi, that is going to be tan inverse of y dot over x dot. Right, because we don't want tan phi, we want phi, so that we can do the derivative. Okay, everyone okay with that? All good. Okay, so now we want this first bit, d phi by dt. Now, there's no t's on this side, but we know y dot depends on t, right? Because it's y of t. And x dot also depends on t, right? Because it's x of t. So we're going to do d by dt on both sides, and then deal with the chain rule and product rule and so on that side. So d phi by dt. That's going to be d by dt of tan inverse y dot over x dot. Okay, so we're going to have to use the chain rule, and then we're going to have to use the quotient rule. Okay, so the derivative of tan inverse of x, that's 1 over 1 plus x squared. So in this case, it's going to be 1 over 1 plus whatever is inside there squared. So that's the derivative of arctan times. And then we need to do the derivative of the inside, but that's going to need the quotient rule because we've got y dots at the top we need to do the derivative of, and x dots at the bottom we need to do the derivative of. Okay, so times d by dt of y dots over x dots, and here we need the quotient rule. Okay, so we'll do that in the next step. So we're going to have 1 over 1 plus y dots over x dots squared times, and then the quotient rule, that's going to be the derivative of the top. So it's already y dot, so the derivative will then be y double dot. Okay, then, so that's like your f prime and then g, so times the bottom, minus, and then the g prime f, from the quotient rule. So the bottom is already x dot. We do the derivative again, so that's going to be x double dot. Okay, and then times the f, so that's just y dot. All over g squared, so the bottom squared. Okay, so that's just using the quotient rule there. Now we can simplify this a bit. X dot squared, we can multiply onto this first term. And then we can keep the numerator the same. So we're going to have y double dot, x dot, minus x double dot, y dot, over x dot squared times 1, that's just x dot squared, plus, and then we have y dot squared over x dot squared, so that cancels, and we're left with y dot squared. Okay, so this is d phi by dt. So let's just write this out again. So we have y double dot x dot minus x double dot y dot all over x dot squared plus y dot squared. Okay. Now remember, this was just half of the problem because it was d phi by dt, dt by ds. Okay, where s, that was the length, the curve length. So let's figure that out, the dt by ds. To do this, we're going to do a little sketch of the curve, and we're going to zoom in on a very tiny bit. So we've got our curve here, and then this tiny little bit we're going to zoom in on. And we want the length of the curve, right? S, that was the length. So that's this tiny little bit here. Okay. Now, if we zoom in very, very close, that curve length becomes flat. Okay. So you zoom in very, very small. That little curve bit ends up becoming a little small flat line, which we can call ds. So s, that's the length. ds, that's just a little tiny piece of the length. Okay, what about the other sides of this triangle? Well, horizontally, that's x, so that's going to be dx. Vertically, that's going to be y, so we're going to call that dy. Okay, so again, we're going to zoom in, and that's going to give us this triangle over here. Okay. So from the curve, it's a bit curvy and so on, but if we zoom in a whole lot, we can draw this triangle at that point. Everyone see what we did there? Okay. Now we have a right angle triangle. We can just use Pythag. So ds squared is going to be dx squared plus dy squared. Okay. Now, remember back when we did differentials, you know, the du and all of that stuff, dx we can write as dx is dx by dt dt, right? You know, from just differentials. And dy we can write as dy is dy by dt dt. Okay, that's just from differentials. We covered that long time ago. Now dx by dt, I'm going to write that as x dot. And dy by dt, I'm going to write that as y dot. Okay. Now I'm just going to substitute that into this equation here. So we're going to have ds squared is dx squared, so x dot squared dt squared. And then dy squared, that is going to be y dot squared dt squared. Okay, so I've just substituted the differentials. Now both of those have dt squared. I can factor that out. Okay, so I've just factored out the dt squared. You could probably guess what we're going to do next. Take the roots on both sides. We took the roots on both sides. Now, we got this expression here for the differential ds, but what we wanted is dt by ds. Now we have that. We've got ds, we've got dt. What we want is dt by ds. So let's just do a little bit of cross multiplying here. So 1 over root x dot squared plus y dot squared will be dt by ds. Okay, so just taking the thing to the other side. And finally, we can put everything together. So d phi by ds, that was d phi by dt. We did that earlier. dt by ds, we just finished that over here. So d phi by ds, this is going to be, or we can put the absolute value, okay, from the beginning here. Just put the absolute value there. So this is going to be absolute value of that numerator we had before, the y double dot x dot minus x double dot y dot. So you can see how they alternate. So you got two derivatives of y, one derivative of x, two derivatives of x, one derivative of y. So they swap there. Okay, and then all of this is divided by x dot squared plus y dot squared to the 3 over 2. Okay. Any questions on this? You're all good. Okay. So last thing for today, little homework problem. Okay, so what you're going to do for homework is start off with definition number 1 that we had and show that that gives you this definition number 2. Okay, so from number 1, you're going to put in your position vector as x, I, y, j, substitute everything in and try get to the side here. Okay, so I'll just rewrite it from what we had earlier. So remember the k, that was the length of t hat prime divided by the length of r prime. Okay, we had that definition before. Show that this will give you what we have over here. So show that from this, we can get to this. Okay, divided by x dot squared plus y dot squared to the 3/2. Okay, you can sort of see how that works out. So in the bottom there, that's the speed. Remember, that's your x dot squared plus y dot squared with the root. So you can sort of see how that works. And in the top, that is t prime. T was the velocity vector. So you're doing the derivative of the velocity vector. That is the acceleration, second derivative. And there in the top there, we have the second derivatives. Okay. So for homework, show that you can get from this first one to the second one. Okay, because they give you the same curvature, you should be able to get from one to the other. All right. Any questions on what we've covered today? All good. Okay, so tomorrow we're going to continue with this vectors. So velocity vector, acceleration vector, and so on. But we're going to do that in 3 dimensions. So in 3D, we've got something like this. So let's say your particle's over there. You're going to have your normal velocity vector. You're going to have a normal vector. And you're going to have a binormal vector. So this will be your T, N, B frame. T, N, B frame of reference. So you all know what a frame of reference is. So I could be standing here. I choose that to be X. I choose that to be Y. And I choose up to be Z. Right? 3 perpendicular directions. That gives you your frame of reference. For a particle moving along a curve, we can also define a frame of reference. So one of the directions will be T. That's the velocity vector direction. Another direction will be N, that will be normal to the curve, so orthogonal. And then finally B, that will be orthogonal to those other 2. Yeah. And as the particle moves around, does its thing, this frame of reference will change as you go around. Yeah. So at some other points, let's say over here, we're going to have T, N maybe over here, and B orthogonal there. Kind of moves around and the frame changes. Okay, we're going to look at these 3 vectors tomorrow. Okay, so you can check on Wikipedia. It gives you a nice breakdown of this. So just say TNB frame. You should see this, but we'll go through it tomorrow. Then next week, we're going to finish off with parametric curves by looking at the length of the curve. Okay, so if a particle starts at t equals 0, ends at t equals 10, how far did it actually travel? Okay, so what is the length of the curve? Yeah, that we will cover next week. Any questions on what we've covered today? Oh, good. Okay, and again, please look at those extra notes for the motion along a curve questions. Okay, very similar to what you covered in physics, but just as some extra work, you can look through that.